welcome people to the technical track systems and buildings. It will take a few or half a minute for all of you to be able to click yourselves in. So hopefully you're in by now. Hello, I'm Henry Vandermark. I will be the moderator along with Cynthia Sikora. Cynthia is a ACES intern and a recent graduate of the University of Illinois, having studied natural resources and environmental science. I run a company, Solar Wave Energy, monitoring many types of solar thermal systems, and have worked in that area for about 40 years. I attended my first ACES conference, Passive 78, a conference focused on passive solar energy, where ACES had the audacity and intelligence to put both architects and engineers on the same stage. After sparks and egos subsided, they learned to share technical experience to better understand solar design issues. It worked. Teamwork is something that this country is actually known for, and ACES creates a platform for people working on technical solutions to get to that 100% goal. So today it's my pleasure to be viewing presentations along with you and having technology challenge us. A little bit of housekeeping first. You've been on sessions earlier. There's a Q&A section and a chat section. You can use the chat to make comments during the presentation. Any of the questions should go in the Q&A. We're limited in time here, so there'll be room for a couple of questions after each speaker. And then we can migrate afterwards to the chat area afterwards. So if we queue up first speaker, James Hall. James, are you on?
It looks like he's on mute.
Mute? Okay.
I'm unmuted.
Perfect.
Good.
Are we going to try to begin?
Yes, please.
All right. Welcome. I'm pleased to talk today about a national database for resource assessment. It's been compiled from ground-based solar observations. In the past, nearly all the satellite nearly all of the solar resources come from satellite-based sources. The National Solar Radiation Database is an example. There are several other companies that offer satellite-based resource. The advantage of the satellite resource is it does have global coverage, but it's somewhat limited in accuracy. And so to compensate for that, it's often common to put in a custom ground site for 1 or 2 years and use the data from that ground site to ground truth the satellite data. There's also very few research quality sites. But today we're going to talk about a new solar resource based on measurements, ground-based measurements from professional sites, has complete US coverage from 2005 to the present. And we're going to show you today that it's more accurate than the National Solar Radiation Database is. We call it the US Ground-Based Solar Irradiance Database, or GSID. I think all of you are aware satellite-based resource passes through a very complex model that converts cloud images into irradiance estimates. The GSID is different. We simply take actual measurements from professional sites around the country. And of course, since it's raw data, many of these measurement sites may contain errors. Rather than just rejecting all these measurements because some of them may have errors, we use artificial intelligence techniques to filter out the errors. I guess I should have introduced myself at the beginning a little bit, but I have a PhD in artificial intelligence. And we're really data scientists rather than so much solar radiation scientists. And so this is our expertise, is taking data, cleaning it up with artificial intelligence routines. The GSID is composed of ground-based observations from over 100 different overlapping networks. And the overlapping part becomes critical as we try to determine whether one site is functioning correctly or not. Over 7,000 sites across the United States. All these sites have professional equipment. They're professionally operated. They're run by federal agencies, state agencies, universities. On average, the separation distance between a site is 37 kilometers across the United States, somewhat more dense in more populated areas and somewhat less dense in the central part of America. Two important characteristics of the GSID: it has better spatial resolution in some very key areas of the country. For instance, in California, we have an 18-kilometer average spacing between sites, over 1,300 sites in California. Other researchers have shown there could be some significant errors in satellite data in California, particularly in the coastal areas and mountainous areas, areas where you might have microclimates. So it's important to have these ground-based sites in close proximity in states like this. Also, the GSID has no parallax errors. Parallax happens, I think most of you know, when the apparent shadow on the surface of the Earth from a cloud is not where the actual shadow is. This tends to occur especially in the early morning, late evening, when the zenith angle is quite high. Because of these errors, early morning and late afternoon observations weren't included in the original error calculations of the National Solar Radiation Database. Here's the backstory and how we got here. You probably figured out by now we have come from a very different path. Just before the turn of the century, we were building artificial intelligence models to forecast the stock market and do stock selection on Wall Street. That evolved into artificial intelligence commodity models. And we built those models to forecast crop yields based on daily crop growth. As we began to exercise these models, we quickly discovered that our models worked a lot better with ground-based solar observations than did with satellite observations. And so that led us to build our own system for ingesting all of this ground-based satellite information, building the AI algorithms to filter and clean up the data. And the result is the GSID that we have today. One of the key elements here from artificial intelligence is a concept called sensor fusion that most of you are probably aware of. Sensor fusion occurs where you take data from different sensors that are seeing the same event, and then you combine that data in such a way that the overall uncertainty is improved. Self-driving cars, for example, have a suite of sensors on them. The data is combined to plot the path and plot the speed. We do many of these same kind of things. Here's a very simple example. So simple sensor fusion can be done with a simple filter. On this day, that was a clear sky day in California, we simply looked at the daily average for all of the surrounding sensors. You can see they're pretty close together, except this one right here in Sacramento was malfunctioning. So we removed that from our data stream until we see that it's functioning correctly again. But how do we know it was a clear sky day? Well, again, the data will tell us. Here's 4 sites in Kennewick, Washington, surrounding. We simply plot all of the data we have over a multi-year period here. You can see it begins to form an envelope, and you'll see the boundaries of the clear sky events. If you're on the edge of that boundary, you have a clear sky event. If you're above that boundary, you have an error. So in this way, we can identify clear sky events. We can identify sensors that are beyond what you would expect on a clear sky day, and again, remove those from the data stream. We do the same thing for any location, any time of day. Here's just a generic example of what you might do if you wanted to see if your sensor was sited correctly. Find the clear sky envelope, as I mentioned. If the sensor was being blocked by a tree, you would see it dip below the clear sky envelope on a clear sky day. If it was tilted, you would see it dip below and then above. So there are many different AI algorithms that can recognize these patterns and again, clean up the data for us. Here's a little more complicated example. This was in Mississippi. You can see we had 4 nearby sensors that were tracking very closely together until right here on this day, the one in red failed. It sputtered a couple of times. Finally, it was replaced right here on this date. But now it's not tracking with the other sensors. So we have to determine, are these 3 sensors soiled? Is this the correct answer? Or is this one miscalibrated when it was repaired? Again, we fuse data. So we bring up the precipitation history, fuse it with the GHI history. We can see that there were significant rain events during this period. So highly unlikely that all 3 of the other sensors were soiled. Most likely this sensor wasn't calibrated correctly when it was reinstalled. We remove it from the data stream, and in fact, it was almost a year later that it was actually, the calibration was repaired. So all of these techniques are pattern recognition. A skilled practitioner can do that manually on small data sets, but if you've got a huge national database, it requires some kind of artificial intelligence routines to perform those kind of functions. So how do we validate the GSID? Well, we looked at how the National Solar Radio Database was validated. It was done by comparing the satellite observations that they had with NOAA's SurfRed network, high quality research from the SurfRed. And so we replicated that same validation technique for the GSID. The only difference that we had is that in the validation, they eliminated the early morning and late afternoon observations, as we mentioned, because of high errors. And in place of that, we just eliminated observations below 50 watts per square meter at the SurfRad sites. In effect, it's the same. We took out the early morning, late afternoon observations. The result, the GSID has lower bias error than the National Solar Radiation Database. You can see typical bias error at the hourly level is about 2.4%, much less than that in the GSID. At the daily, you'll see much less bias, again, much less bias along the way. So the GSID has lower bias error. If you talk about accuracy, there's 2 ways to consider accuracy. One might be mean absolute error, another might be uncertainty. If you like mean absolute error, the blue line on the top is the National Solar Radiation Database, about 21% average error, typical error at the hourly level. Half that for the GSID, about 12% mean absolute error for the National Solar Radiation Database, 8% daily. And as you get down to the monthly and average, monthly and annual levels, they're about the same. You see that same trend, and uncertainty, if you like to use uncertainty as a measure of data accuracy, very similar at the monthly and annual levels, but roughly half the error or half the uncertainty at the daily and hourly levels. So significantly better accuracy at the hourly and daily levels. You can see better spatial resolution. For example, if you look around the area of the Mississippi Valley, or spatial resolution that you might find in the National Solar Radiation Database, again, because of the large number of sites that we have. So better temporal accuracy, better spatial accuracy. So in summary, there's a new solar resource that's available. It's built entirely from ground observations. We use quality control. We quality controlled it using AI technology, as we've explained, some of the algorithms. It's been validated using the same methodology that was used for the National Solar Radiation Database and shown it to be more accurate. And this database is freely available. You can get it on our website. You can download for free daily observations for the last 15 years, or you can contact us and we'll work with you on hourly observations. So if there's any questions, I'd be happy to take them. Here's how you can contact me if you'd like some additional information. Thank you.
So are there questions that have come into the chat or not? I have one question as far as, is that all history data, or what about real time as far as weather data and things like that?
Yeah, we have new real-time data available. We gather the data every Monday. So we have hourly and daily data available real time. The data that's available on our website for free goes through from 2005 to 2019.
So is that distributed out to other third parties and APIs and things like that out there?
Right now, we're just a small company. Right now, you could get on our website, you can request the data, and we'll email it to you.
Yeah.
Okay. So it's semi-automated. We would love to partner with somebody to make it more widely used and widespread, but we haven't done that. So if you know anybody, Henry, let us know.
Okay, no, I'd love to have a conversation. Thank you very much.
You bet.
And we should probably tee up for Nir,
Okay.
I think. We're all learning about virtual, and it's challenging.
Yeah, screen sharing and all these things.
But hopefully by the time the pandemic is through, we will not have to have too many more conferences virtually.
So should I start?
Yep, please do. Yeah.
Okay. Sorry?
I'm just saying, if you can give a brief introduction, just be shorter than for me to do that.
Yeah, so let's see. So I'm Nir Krakauer. I'm a professor at the City College of New York. And I've been working on different climate and forecasting issues, including renewable energy related ones, which I'll be what I was talking about today. The last presentation gave a good sense of how the average solar resource in this case varies across the country. But in addition, of course, solar and wind both vary within a given spot depending on different weather phenomena, as well as the energy demand that these supplies contributing to. The photo is from somewhere in northern England on a fairly sunny and windy day. And of course, there is a daily cycle of sunlight and often of wind also. There's an annual cycle, but it can also be changes from week to week. Let's say if there's a front passing through, so it's cloudier or windier than usual. There can be months which are different than the climatology for that month. So it can be beneficial to understand what these fluctuations come from and to be able to predict them as much as they are predictable. This is a study by the Perez outfit from Minnesota using electricity generation data there.
Slides are not advancing here?
Yes, advancing. Can you see my slide?
Your screen is freezing.
It's what?
It's freezing, your screen.
How?
Okay, now it's good, I think.
So for this Minnesota case, we can see that there is a peak in variability for the PV generation at a daily time scale. For the wind, there's more of a peak at a multi-day time scale as fronts go through. And then there are also peaks at a seasonal time scale, but there's a variability at all these different time scales. And then the dashed line shows that you can reduce the variability in most time scales if you combine PV and wind resources across the state. This is an example of the kind of variability you might see in a given month compared to the average for that month for all other years. So using a reanalysis data set, it might be interesting to use some more observation-based data set like the one we just talked about. So here, for example, it was sunnier than usual in the northeast US and eastern Canada, and cloudier than usual in the Midwest. And similarly to our wind fluctuations, they were bigger in the oceans because the winds are more consistent and powerful, typically over the oceans than over land. One such example of a fluctuation in renewable resources that was noticed by a lot of operators was this wind drought that took place in the first half of 2015, where the winds were much slower than average over a lot of the western and southern half of the United States and nearby areas.
Your screen is still not progressing. Okay, there we go.
Okay, that's interesting. So when I'm in slideshow, then that seems to be not visible. Okay, so I guess I'll go back to the default window. I published on that and some of the factors behind that, but that caused a lot of losses for wind operators. This is an example of a spatial correlation between spots that give you a sense of how big these anomalies are spatially typically. So the correlation goes from 1 at 0 kilometer distance in the upper left corner of each of these plots down towards 0 at long distances. So if you're far enough apart, then these monthly anomalies tend to not be correlated from between places which are far apart from each other. And typically the length scales are about 1,000 kilometers. They're a little bit shorter for solar than for wind. We can correlate these anomalies with differences in other aspects of climate, like the pressure field. So we can see, for example, so this is looking at just at a point near New York City. That's where my cursor is now. Where with solar, the correlation with the pressure field is negative with the pressure east of this particular point, and positive with the pressure southwest of that point. With wind, it's more just negative with the correlation with the pressure east, and positive with the pressure far north in the Arctic, Greenland. Sea surface temperature is something which is more persistent and potentially predictable than the atmospheric pressure fields. And we see that there is some correlation between, again, just using that same point as an example, the solar and wind fluctuations at that point and the sea surface temperature field. The places which are but yellow, where there's a positive correlation between warm temperatures and the sea surface and higher wind or solar resource for a particular month than average. The dark blue is where there's a negative correlation. And for example, the wind drought, we were able to connect with anomalies in the pressure field, in this case, the geopotential field in the upper figure, and with the sea surface temperature field. So there was this warm blob in the Pacific off California and the West Coast that led to these persistent pressure patterns and weaker wind over the Western US. So then the question is, if we understand something about how these anomalies in solar and wind resources correlate with different aspects of the climate, how predictable are these aspects of the climate? That gets us to the idea of seasonal forecasting, which is typically, as in this graphic, predicated on there being persistent aspects of the climate system which don't change that much from month to month, and therefore can be predicted to some extent. So these are things like sea surface temperature, because the sea has a lot of heat capacity, so the worms are cooled slowly. Soil moisture, again, the soil can stay wet for a while or stay dry for a while. Snow cover, because snow takes time to melt. Might have things like aerosol that might be related to volcanoes, or things like the shutdown of airplane flights this year. And having these surface temperatures, which are possibly predictable, changing from month to month, can affect patterns of weather over the continents through these teleconnection modes, such as El Nino and the Pacific North American oscillation that's shown on top here, that changes the pressure pattern over the Western US. So there's two basic approaches for seasonal forecasting, which can be combined. So either using statistics, seeing what patterns that are predictable correlate with anomalies in the past, and then developing a regression model to predict the future, or dynamical climate models, which simulate the climate using the differential equations of fluid mechanics, and can be run for a few months in advance and hopefully have some skill in telling us what the climate is going to do a few months in advance. So with computers becoming more powerful, this dynamical approach has been tied up more, and the skill has been increasing to some extent. And again, the idea is that we're running climate models starting with present conditions to simulate the next few months. We can do an ensemble of ones that gives us a spread of the different possibilities that we might have in the next few months. And that's can potentially capture changes in movements of air and water in the ocean and land, and factors like snow and vegetation. The models that do seasonal forecasting in the US and Canada have been aggregated by NOAA into this North American multi-model ensemble, NMME, where each of these models is run every month for up to about a year ahead. And they generate forecasts which are posted in a central location that anybody can download and analyze. Unfortunately, they don't output the things like solar radiation and wind speed. They primarily output temperature and precipitation currently. So that may still help us in predicting wind and solar fluctuations, in that, as I showed, the sea surface temperature has some correlation with wind and solar fluctuations, which will depend on where you are, what the pattern of correlations is. And the sea surface temperature is pretty skillfully predicted by the NME models after you do some averaging and weighting of these models. So you can see this paper from 2019 for more details on that. This map shows that the pattern of the skill score, where again, there's much higher correlation with temperature over the ocean than over land. So it's the more predictable aspect of the temperature, which we might be able to use for wind and solar forecasting. The figure on the right shows the performance of NME models in predicting some big flood and drought events. So they had some skill, possibly in some cases. So in conclusion, again, we can have this variability in the solar as well as wind resource, as well as these spatial patterns, which we can find for a particular day or a particular year or an average of years. And it's a challenge that is starting to be worked on to predict these fluctuations over this longer time scale. So we already use, of course, nowcasting and short-term forecasting in managing renewable operations for giving us a sense of what the output will be a few days in advance. So this may give us a chance to get information about the output fluctuations a few months in advance. So I'm going to stop here, and my website has the full text of these publications that I mentioned. You can also email me if you have more questions or ideas. Thank you.
Great, thank you. And I think we have a minute or so for questions left on that. Are there any in the queue that?
Yeah, so there's a question from Dorothy, and it says, what is the hope from doing these analysis?
Yeah, so the hope would be to be able to manage power supplies and the energy supplies over longer periods of time. So for example, if you have a hydroelectric component to your power grid, you could decide how much water to release depending on whether you expect your output of wind and solar to be higher or lower than normal over a given season.
Wonderful, thank you. Are there any other questions? Nope.
Don't see any more. I see some that went for James, but you can go in the room afterwards. So if we set up for the next one,
Yes, it's me.
your screen shared?
Yes, I will. Okay, wait a second. Screen share. You can see my screen now, right?
Yes.
Yeah, that's full screen. Good.
Can I start?
Yep, please do.
Oh, hi. Actually, my name is Ehne Zhang. It's a Chinese name. It's fine. And I'm from Penn State University. I'm currently a PhD candidate. And with my advisor is Dr. Julian Wang, and we have a laboratory called Archie Lambda Laboratory. So today's presentation, I'm just introducing our recent research about the energy saving analysis of window coated with spectrally selective NIR glazing films in window. And today I'm presenting I'm first introducing our program and our approach, and give a little bit hint about the mechanism, and also our experiments. Our goal for today is also sharing some of my calculations and analysis for our approach. So as we may all know from, and you can see from the PowerPoint, there's we are working on single pane window now, because there's still 30% to 40% of single pane window especially on old buildings and residentials, and that is response to over 50% of total energy lost through window in America. We are particularly working on spectral photothermal coatings, which this project is supporting by NSF to understanding the thermal and optical behaviors of near infrared selective dynamic glazing structures. So our goal is using this photothermal coating to increase the thermal behavior of the glazing system. Particularly now, we want to increase the window temperature, surface temperature in winter, so that to reduce some of the heat transfer between the indoor room and also outdoor room. This is our gap now. The single pane compared to double pane. When we want to enhance the single pane, usually we have the researchers have two approaches. One is some of them using adding insulations, and our approach is adding selective a spectral selective coating to enhance the thermal behavior of the window. So our goal is to approach a so-called idealized window to save some solar infrared and visualize. This picture is to save some energy in summer and also in winter. As we can see here, for the whole spectral distribution, there's the yellow part is the visual part. That is the energy, but the near infrared part has over 50% energy distribution there. So if we can have some, well, our approach is using spectrum selective coating to absorb some of the heat in the around the near infrared part, so that we can increase the window temperature. So our solution is the photothermal window. And also you can check our project on the website listed and here. So from the experiment stage, our group is cooperating with other material scientists. They have developed this photothermal coating, spin coating, and they have got samples which is small scales, and our participations are now making scaled physical models and testing the spectral response, such as emissivities and transmissions. That's both two parts. The energy will absorb or transfer with the window system. So in our lab, we have after we make the physical model, we have the thermal chamber to simulate the room temperature, and the solar simulator, we can simulate the solar spectrum there. And this is the approach from the material side of materializations and characterizations to architectural engineering side. We building models and doing data collections to see if we can save some energy there. So for this photothermal, it is so-called iron 3 octane 4, and this is another nanoparticle, and this mechanism is based on the atomic energy absorptions and heat generations. The deeper mechanism is based on a trajectory structure which can perform like a whole material, and you can read here. But it's not my expertise. It's my colleagues with material science background will more familiar with this material. And what we do actually is setting up the experiment boundaries and understanding the experiments. And our experiment is using the solar simulator, which is a 150 watts lamp, and setting up the glass to simulate the window with our photothermal coating, which we want to test the temperature increase, so we can see how the performance of the photothermal coating, which now we have tested that the temperature increasing for the photothermal that way can be 5.43 K, which is relative high the temperature increase in window system considered to the environment temperature. So, and also to do this, we have to work on the photothermal heat coefficient to see how the photothermal is transfer this solar energy into thermal temperature increase. The background calculations you can see here is everything. We can converge that that energy absorption into a function of temperature and time, which evolved with the global horizontal irradiance and some of the data connected, so we can convert the solar irradiance to a temperature increase on top of the window surface. In that, we kind of using the air conductivities to calculate the heat transfer between air and the window surface layer, which also considered temperature and the humidity change. In those equations, we set constant indoor room temperature and outdoor temperature in a way to limit the variations. So this is a sample of how we design our sample. This is a simulation results from a software called Optics. This Optics and Windows software is from Lawrence Berkeley National Laboratory. They developed this software so we can freely use to work on optic spectrals and also window simulations. You can, in type 1, we are comparing a low E coating coated on the window, a single pane window, and compare with photothermal coated with this low E coating window. And in the results, they have same U factor, which is reasonable resilience, not really change. But since the visual transfer, the visual transmittance for type 2 is lower than type 1, which makes sense because photothermal has a lower visual transmittance. So you can see that from here that this is a data from optics. You can see the left is transmittance, which is when low structure combined together, the transmittance curve is showing like this, looks like this, and this is the absorption curve, which you can see in the transmitting curve. We have.
You probably need to wrap it up pretty soon.
Okay. How many minutes do I have?
None.
Oh, sorry. Okay, I'll be quick. This is the curve, and this is the temperature the curve difference. And if you can see, it's around 36% of mole absorption for the type 2. And with type 2, we can this is the last page. And with type 2, actually, after calculation, we can save for 12.78 watts per meter of energy. So which is actually is 8.3, which is actually some of the energy saving there. Okay, that's all today. And that's the question.
Thank you very much. I would have some questions, and there's some questions in the Q&A, but I'm afraid we have to move ahead and have those in that lounge afterwards. So I hope you will move into that after this.
Okay, I will stop sharing.
Yeah. Okay. So Mostafa, if you could share yours.
Yes.
And I apologize for not having tools to be able to prompt. We're all learning about these virtual platforms, and the tools are not quite as good as it could be. Is your,
So
your screen up?
it doesn't work again. I don't know.
I saw it for like a second, but if you'd like, I could share my screen. Oh, okay.
Do you see that?
Yeah.
Yes. It's that note thing.
Again, there is a problem.
I can share my screen, and then if you just tell me when to switch the slides, that works for you. It's cut at a weird place. Oh, there.
Now?
Yes.
Okay. Hello everyone, my name is Mostafa and I'm a PhD candidate at GW Department of Electrical and Computer Engineering. And I'm very happy to present my research entitled The Role of Energy Supply, Mobility and Resilience of Solar Integrated Electric Distribution Grids. So firstly, I'm going to go through the introduction, then the methodology will be explained and how mobile power sources can boost power system resilience, and numerical results will be explained. And finally, I will conclude the presentation. So there are several sources of threats to power grid operation leading to electricity outage. Severe weather events, such as flood, hurricanes, earthquake, etc., cyber attacks, vegetation getting in contact with the wires, human errors, etc. Among all these causes of electricity outages, weather event is number one in resulting electricity outages, as you can see in this table. So the end goal is to enhance power system resilience. The first question is that how can we accurately predict high impact, low probability events called HILPT events and their consequence on power system? The second question is that how can we plan to mitigate the effects of such disruption events and reduce the load outages? So speaking of resilience, we have two terms: long-term resilience and short-term resilience. The long-term resilience indicates the hardening of the grid. We can employ the battery energy storage system, distributed energy resources, advanced metering infrastructures, and microgrid planning and formations in order to enhance the power system resilience in terms of long-term. On the other hand, short-term resilience refers to mitigation and restoration. Mobile power sources such as electric vehicles, mobile energy storage systems, and mobile emergency generators can be utilized in the power system along with remote control switches to enhance the short-term resilience. So the research gap that we are focusing is the coordination of mobile power sources dispatch with remote control switches, incorporating the renewable energies like solar energy. So now I'm going to talk a little bit about mobile power sources and how these sources can help us to enhance the power system resilience in face of natural disasters. So following a natural disaster, some distribution lines might be out of service, which cause some isolated islands. Mobile power sources can be routed and transmitted through different islands to supply demanded loads in the system until repair crews repair damaged branches. By doing that, the load outage would be reduced and the power system resilience would be enhanced. So the proposed framework of power system restoration includes 3 different stages. In the first stage, or before a HILP event, we need to gather predicted load information, distribution system characteristics, available solar forecasts, and eventually mobile power sources configuration. The second stage includes the damaged branches evaluation and the repair strategy. And finally, the last stage is all about the mobile power sources dispatch and the remote control switching actions. So the proposed formulation includes the objective function and several constraints. The objective function is is minimizing the load outage and curtail solar power. Several constraints need to be added into the optimization to ensure the radiality of distribution system and node power balance in all nodes in the system. So I'm not going to go through the details of the formulation. So now I'm going to talk about the case study and numerical results. So we implemented the proposed methodology on the IEEE 33 node test system to show the effectiveness of the proposed framework. The test system includes 37 distribution lines, including 5 tie lines. So I mean tie lines, the lines which are normally open, like this line, which connects node 25 to node 29. So 5 tie lines, 3,715 kilowatt demand load in the peak time in 32 load points, 3 charging stations, 3 mobile energy storage station, 8 remote control switches, and a PV with 500 kilowatt located at node 10. So here and in a few slides later, I will show the restoration procedure utilizing mobile power sources in the system. For instance, here at time 3, some branches are out of service, like this branch, and so on. So some load points are disconnected from the main grid, and what we need to do is to transmit these mobile power sources that we have in the system. So electric vehicle is routed to node 33. The mobile emergency generator should be transmitted to node 29, and the mobile energy storage should be connected to node 15 in order to supply some portion of demanded loads. As you see, some part of the network is supplied by mobile power sources at T4, so we see more green lines, like more supplied loads here. So at T9, for example, some damaged lines are repaired by repair crew. So some MPS should be routed differently. As you can see, this should be routed to node 29. Then at T15, for example, the electric vehicle should go to node 5 to be charged, since its state of charge reaches to the minimum level. And at T18, it goes back to node 33 again to supply some other loads. So as you can see, there are some damaged lines still in the system. However, we are supplying all loads in the system. So all load points are supplied by either the main grid or the MPS. So in order to evaluate the solar energy penetration impact, we consider a PV farm at node 10. And we consider different scenarios to evaluate the accuracy of the results. In case one PV is connected to grid at T7, for example, here in case 2, you can see the PV can be connected to grid at 10. And likewise, in case 3, PV is connected to grid at T5. So in all cases, the results reveal that considering PV in the system can result remarkably in a fast and more restoration strategy. So considering solar energy, we can get system back to the normal condition faster, which result in a more resilient system. However, the switching actions and the MPS routing and the schedule don't change. So as you can see, the green lines show the case considering PV can restore more loads in a shorter time period, and the switching actions and the configuration of mobile power sources considering PV and without PV are depicted here. So as you can see, the green line is higher than other framework. In order to evaluate more the accuracy of the results, we consider different cases. And in all cases, the results showed that considering PV in the system can result in a more resilient distribution grids. So as a conclusion, we propose an efficient strategy for routing and scheduling of different types of mobile power sources to restore the load outage following a natural disasters. We saw that the system can be affected significantly by solar energy if they are correctly imported into the optimization. Thank you for your attendance, And if you have any question, please feel free to contact me by this email address. Thank you so much.
Thank you. So, questions in the chat?
So Dorothy asks, is the system based on an actual city? If not, how did you determine what size and loads should be studied?
So we can consider actual test system as well, but because we need to run a lot of scenarios and we need to gather a lot of information, we prefer to evaluate our proposed formulation on a standard test system. So our proposed formulation was implemented on a standard IEEE 33 node test system, but it can be implemented on any test system if you have any data or any configuration for your system.
All right, thank you. Okay, there's another question from Chris. It says, this is so interesting. Do you imagine a fleet of MPS to be employed in any city to accommodate emergencies?
Exactly. So actually, these days, the utilities, the electric utilities are using these mobile power sources in the system. So, and this is a very hot topic these days to employ these mobile power sources in face of emergencies. In any case that we lose some portion of our demanded load in the system, we can route and we can use these mobile power sources which are available in the system and supply some portion of demanded loads. But the point is to because they are they cost us, so we need to route these mobile power sources very carefully. So we need to run a very detailed optimization to get the global optimal solution in order to minimize the cost, in order to minimize the load outage and increase the efficiency of these mobile power sources.
All right, wonderful. There are more questions in the Q&A, but for the interest of time, we should probably move on. But if you could visit the Q&A, that would be great.
Okay.
Thank you. And if you should, Rahim, if you can cue up your video, and hopefully the sound and video both work seamlessly.
Hello, everyone. My name is Rahim Khoie, and I really enjoyed these amazing talks by all these PhD candidates of ours. Really good work, everyone. I am a professor at the University of Pacific, and being a professor, you become very comfortable talking in front of people, but sometimes you become too comfortable, and usually you think you have all the time in the world. So what I did was I actually recorded my presentation, and it was 15 minutes. And then I removed 5 minutes worth of saying, and also mistakes and repetitions and all that. So with that, I'm going to share my screen and run this video. Good afternoon, everyone. My name is Rahim Khoie, and I am presenting a paper on the carbon footprint of wind. I'd like to acknowledge the great work of my two graduate students, Andrew Bose and Josh Saltzman, who actually did this work. In 2018, after 10 years of decline in the US total emissions, the emissions in the US went up in 2018 by 2%. This is bad news. The good news is that the wind is on the rise in America. In fact, in 2020, first quarter, the total wind capacity of the US reached 107,000 megawatts, mostly in the sweet spot of wind in the US, which happens to be the great state of Texas. All right. The bad news, however, is that according to NASA and NOAA, the CO2 contents of the atmosphere has reached 412, 413 parts per million. Warning by NOAA in 2018 in this very conference that it's time for us to remove carbon. In 2019, US produced 286 billion kilowatt hours, about roughly percent of total US electricity production from wind. The question is, how much emission was involved in this production? All right, so this is what this paper is about. It is actually a rather complicated process to actually determine the precise exact CO2 productions, in large part because, first of all, there are many, many steps involved. The excavation and extraction of raw material, to production of supplies, to manufacturing of the windmill, to transportation and construction, to the operation and maintenance, to decommissioning it and actually removing the waste, not only after decommissioning, but also during the actual operation and the recycling and the landfill. And I'm not proposing that I have considered, or anyone for that matter, has considered minute details of all these processes. Three quick models. One is what is the lifetime electricity production of a windmill? Well, what people mostly do is they use typical meteorological year 3 data from NREL, which actually lists almost hourly typical average production, average wind speed, and you can actually use that. Raw material, for emissions of raw material, I shall use a process analysis, and for the manufacturing, transportation, construction, and overhead, I shall use an environmentally extended input-output model, a model that is used by almost everyone. All right. A typical windmill is about 1.3 megawatts. We have it is in Nordics, and we put it in Texas. Quickly, for those who like to see some mathematical equations, the power that's generated by wind is proportional to the cube of the wind velocity, except that the wind velocity at the bottom and top of the blades are not the same. The wind changes with height. The wind speed changes with height, so this equation allows you to actually compensate for that speed differential between the top and bottom. Quickly, the energy produced would be a power curve, which is a curve as a function of wind speed, times 3,600 seconds per hour, and then you sum it over all the hours, starting at 1 o'clock on January 1st, ending at 12 o'clock on December 31st, all right? This is the speed power curve of Nordics N60. For the raw material used, we actually use this process analysis, which is pretty much list the amount of CO2 that is produced per kilogram of these various raw material. Nordics give us the amount of steel and all that plastic and all the stuff that goes into the construction of the wind. All right, the equations are simply easy. The CO2 is the mass, which are, we know that data from Nordics, and the CO2 emission factors, which I just listed. For manufacturing, transportation, construction, and overhead, we use a widely used model called environmentally extended input-output analysis. A number of great economists actually have put together and come up with these factors. So for instance, this number, emission economic factor, is how many grams of CO2 per dollar is in various sectors of the economy. So these factors are listed here. For if you know what is the price of the copper and copper-based alloy that went into this system, You can, and if you know the price, you can actually just go and multiply that by this factor, and that gives you the amount of CO2 that is actually produced. All right. The results for raw material consisting of steel, plastic, concrete, copper, and all that amounted to 9.5 terajoule. And for emission, it was 715 million grams of CO2. These are the raw materials. These are the results of the processes, transportation, construction, overhead, manufacturing, and that would be 16.08 for the energy and 1,155 for the total CO2 production as a result of construction and operation of a windmill for about 20 years. All right. Putting these numbers together, you come up with a lifetime, total lifetime input energy, the amount of energy it takes in 20 years to build, to construct, to operate, for 20 years. And the total CO2 is indeed this number, 1,870 million grams. Finally, if you put these numbers together and divide that by the total production in a lifetime of about 20 years, what you get is about 55 watt hour per kilowatt hour. And more importantly, the intensity or the amount of CO2 that is produced per kilowatt hour is 14.45 grams. All right. Now, if you compare this to the electricity generated from coal, this number, 54, is 157 watt hour. And the CO2 emission of coal is 792 grams. 14 grams versus 792 grams. An amazing drop in CO2 emission. But if we are actually talking about totally carbon neutral energy production, we need to actually, even though this number is significant, this number is only 1.8% of this number, but still it is a number. By the way, the reason we know, even though we haven't included minute details of all these processes and all that, we know our numbers are correct because they are these results are consistent with those that were reported by others, although they are slightly higher than what others have actually reported. In conclusion, wind produces 98.2% less emission compared to coal. However, and it uses 65% less energy compared to coal. However, it does produce 1.8% emission. 1.8% is a very small number compared to 1.8% compared to coal is a very small number. But if we are producing 286.6 billion kilowatt hours of wind, which is roughly 7%, that's 4.12 million tons of CO2. The expectations are that by 2050, half of US electricity production would be by wind. Well, if you want to flag me on this number and say, no, it would be 40% wind, 60% solar, I'm okay with that too. But remember that these numbers, if you, so this is going to be 7 times, and these are annual. This is every year. So as this number goes up, this number goes up. So expect. Therefore, we need to plant trees, which is something that can readily be done because look. If this is your wind farm, you can actually plant trees right here. And then it would be totally carbon neutral. These are my references. And I look forward to your comments, to your critiques, and to your questions. Thank you so much for your attention.
Did you see, in spite of that, I still had so many But anyway, thank you, everyone.
Thank you very much. It's always great to have life cycle cost in carbon. It's good. It's good to see that. It's all the technologies need to show that.
Believe it or not, I have some kids who are working on solar. Everybody says solar panel on the roof, solar panel here, there. They are not as carbon neutral as we think. Of course, everybody knows that. But anyway, maybe 2021.
Yes. Good.
There are actually two questions in the Q&A. We can do one question for the interest of time. Dorothy asks, how typical is it to use different wind speeds in the swept area for the annual energy output?
Well, thank you for that question. It actually depends on the location. Usually windmills have a cut-in and a cut-out speed. Cut-in is usually about 4 or 5 kilometer per hour, miles per hour. And the cutout is usually 27 or maybe 30 miles per hour. So you really, it depends on the design of the windmill itself. So again, you need to analyze, that's why we picked this Panhandle of Texas. So that question is actually requires studying and running these models for various other windmills with higher swept area and also the location in which they are installed. We actually took all these numbers so that our numbers are higher than others because we really wanted to have a worst case scenario. For instance, if he had actually assumed 30 years lifespan, which some people do, these numbers would have been smaller and the CO2 footprint would have been less. So it's truly a multivariable system to be analyzed.
All right, thank you. There's actually 2 more questions in the Q&A, but for the interest of time, we should move on to the next speaker. But if you could either visit that or the chat room at the end of the session, that'd be great.
Okay.
Thank you again. And can we queue up the next Regin? I don't see your, are you shared?
I should be there now. Thank you.
Okay.
Let me see if I can share my screen.
Yes. Yeah. Magic takes time.
Do you see a full screen on your end?
Yes.
Excellent. And the transitions are working?
Yep, looks good.
That's good. Thank you for inviting me to this conference. It's the first time I participate. And it was my program director, Cindy Urnes, who recommended I should go to this conference. I'm a registered architect. I hold that registration in Denmark. But I actually teach, I'm an associate professor here in Fargo at North Dakota State University. And I will talk about a house that I designed and refurbished, a building that I bought in 2007. So it's going to be a very different presentation from the other presenters today, but I think you will enjoy it. My objectives are evidence-based deployment and of course strategy. But as you know, there is no strategy without tactics. So do some explorations in the field and let's see what we can do. So here's a building that is almost 100 years old in the top right corner of the slide here. And below you see the refurbished building, more or less 100 years later. It looks like this. And this is placed in an environment where you have plus 80 degrees summer and you're out in the Great Plains of North America. And then, of course, you have winters where it's minus 40 degrees sometimes. And this original building had no insulation. This domestic dwelling was also published a few times. It was in the newspaper, as you see here. And it was also in some magazines last year. And in the references in the last page, if you feel like it, you can always go and check out a little bit more about the efforts that was done here. But this was done more from a design perspective. In this presentation, I would like to talk more about certain very low-key technical aspects. Here is the location, that is Fargo, North Dakota. And what's really interesting is, if you're looking at the red line, is that Fargo, North Dakota is not somewhere up in Scandinavia, but actually it lines up a little bit north of Venice in Italy. And the capital of the United States is actually close to Palermo in Sicily, in the middle of the Mediterranean Sea. And if you take Miami, you end up in the Western Sahara. So my education was very different. I came from Denmark, and that is the blue line. And that is actually taught in such a way that we are very interested in sunlight in that country. And if I zoom back to North America, I end up in the Panhandle of Alaska. This is just some basic facts, but I think you should hold it in mind if you are a designer. So I mounted a huge, massive risolet to the south and also to the north, just to indicate what's going on in this building. This is, of course, cedar, a product you hardly can't find in Europe. If you can, it costs you a fortune. There's plenty of it in North America, and it somehow maintains itself. You can see that it's a lattice system just above the windows and below it in this new facade that has been mounted to the existing house. You can see that it's just packed. The rest of the facade, you can see that there's just wind going through. Behind the cedar, there's a mosquito mesh. Here are some of my early drawings. Here are the additions. I could talk for an hour about this, but I'm not going to do it in this session. So I'll just move on to the next slide. But I think a lot of architects, and actually also a lot of engineers, don't really take this sketch out when they try to collaborate or work together. I think it's very important to do. Even in North Dakota, which is actually quite unbelievable, the sun comes up on the 21st of June to 66.5 degrees. You can actually design a threshold situation on the south facade of your buildings so that the heat stay outside. Of course, you have to mount the glass on the inside of that threshold. We did mount a door on the outside, so it heats up all the cells on the inside of the building, and it's maybe not so efficient in the summer. However, in the winter, the sun only comes up to 19.5 degrees on the 21st of December. But you can, of course, design with it and let all that sun come in and heat up your floor. And the engineers, of course, will call all this thermomass. Here is the idea for the presentation today. Take an existing building and then wrap it another time. A little bit like putting on a winter coat. A house in a house. Ventilation, of course, between the old structure and the new structure is really important. You just simply leave an air gap and assure that you never have any mold. But what I discovered with this building by living in it, I realized that there was a really powerful idea. This is the sub-facade idea and the rain screen idea. And this is what this presentation today would mainly focus on. Let me show you how it was done. Here's the original house to the right. And here you see it almost completed with the house in a house idea. Now there's a lattice system that you see here that is vertical, simply 2x4s. You don't find this in any building codes anywhere in the world. Notice this arrow here and see that there's already a lattice system that has been placed up there. I do not have a photo, but I mounted some virtually here on top of the slide. And if you create this crisscrossing structure just by simple 2x4s, you can have a really efficient passive ventilation system. Your air will then be able to flow behind this facade when it gets beaten by the sun. Do it for the roof, do it for all facades, and tie it into a ventilation box. Actually, all houses have actually a slight, small ventilation cap, ridge cap. You might not know it, but you probably have it on the building you live in if you live in a domestic dwelling. They're very tiny, but just enough to hold a little bit moisture out if there's something that gets trapped behind the rain screen. Now, if you take this idea, this is not a new idea, but if you enlarge that idea and do what I did to this building here, you can have a passive system. This is what gave name to the house. We mounted one of the rooms. This is where my daughters hang out and they watch TV in this cube, the cloud. But if you study a little bit further down, I just want to show you how exactly it's done from a technical point of view, since we are in a session where that is the focus. The existing house is in gray. The new house in a house is the blue with the insulation. The gray has no insulation. But what's most important is, with this idea and in this presentation, is that you create an airflow between your sub facade and your rain screen. And that is somehow demonstrated here by those orange arrows. The sub facade is very often an OSB board. You need to actually apply a lattice system vertically 2x4s in blue, horizontally 2x4s in orange. And then you have a very efficient passive cooling system. Here the rain screen has partly been mounted. Where the ladder is placed, you can see the substructure for the ventilation area. However, the signature is really in the front and in the back of the house, which is here. And there are tiny air gaps right here where you see those arrows. The brise-soleil here is fully mounted, but this is here how it works. Here you actually see a pull, and then the ventilation box actually automatically just makes a pull upwards. So air is simply just being sucked behind the facade where the white arrows are, and the hot air in the summer is just being accessed from the rich ventilation box on top. You know, as an architect, and also most engineers, we don't like to make a lot of holes in our roofs. And there's always a lot of installations that are being poked through. I always thought it was rather silly. And that was my main design objective. But as I lived in the house, I discovered this is actually a very efficient cooling system. We actually had a mechanical cooling for this house, which is never turned on anymore. Here's a little bit more about the technicality. Along the facade, you have also mosquito screen and cooling along the concrete foundations. Here's the references for the publications so far. And then I also should add that the heating cost is now $500 a year for this house. And there's no more cooling costs associated with the building. We have mechanical cooling, but we never turn it on. Thank you very much. I was very happy to join this session and be invited to this conference. It's the first time I've taken this building in this direction. Hopefully there will come some more of it. Let me know if you have any questions. Now I just have to figure out how to exit this and stop sharing the screen. There.
Thank you. It's nice to get a full house to end up the session.
Thank you. And I can see there's one question. And this is about the aesthetics of the house. Dorothy Gehring asked this question. She asked, how do the neighbors like the aesthetics of your home? And yes, I was very concerned about that because I do not like metal myself. And as you know, metal can get very, very hot also. So I had to figure out how to do that. The reason I did it was because I moved to North Dakota and I quickly realized that I just love barns. And of course, a lot of the farmers in the Great Plains use metal for their buildings, and I find them very beautiful. But to actually use galvalume metal, corrugated metal on a domestic dwelling, it's not a good idea. But if you work very carefully with it, you can actually make a very good aesthetics, and it's up to you to judge it. However, the neighbors actually loved it. And we actually had very conservative neighbors, very critical neighbors who came over to me and said, we just love your building. And I think it was the barn associations, you know, associations with the North Dakota barns. We have 2 more questions coming up, but I don't want to take all the time. I can maybe answer them in writing. Should I take one more question here? There's one more. Did you ventilation between the old house and the new? Did you put ventilation between the old house and the new addition? Yes, I did. But that is a very passive ventilation. It just simply organizes itself. Along the last slide that you saw, you could somehow see how the metal was hanging over the concrete. And if you simply just create an air gap about 3 inches, and then you just have to be sure that the air can move the whole way up and along the roof and up into this enormous ventilation box. And just like how you have this, what is it called? And here the engineers have to help me. You know, you're making yourself a T and you forgot about the string, and then there's somehow this effect that the water just poured out. And that's the same for the air. The hot air just simply starts pulling the little bit cooler air away, and then just sucking air from below further up along the facade. It's really interesting. And I highly recommend you to do it on your buildings in the future.
Thank you for that. And then the rest of the questions, it would be great if we could transfer them over to the chat room after this session.
So I'd like to thank all the speakers, and also I'd like to invite all the speakers to help with ACES for next year, and maybe consider being part of the technical divisions, because in a way this was a mixed, as you realize, a mixed session of a number of different types of sessions, from data to full house. And in past years, ACES has had a session for maybe one for houses and one for data, so that there's a technical division which can act as a peer review, a good place for graduate students or practitioners. But it's just something that I invite you all to take a look at and see if it fits your needs and desires. And thank you again for the great presentations. And I applaud, except I don't know how to electronically. But, so I'm not sure how this, yes. It's good to bring and maybe consider bringing your students in, because we need more young professionals, because some of the people have hair that's not quite as light as mine. So that, and you're muted.
I really wanted to reiterate my absolute appreciation for all these young, fresh PhDs. You guys are great work, everyone. You guys are the future of this game. I am right there with Henry. I don't have hair to be white, but if I did, it would have been white. So great job, everyone. We're gonna pass on the torch to you guys. So please do join and do contribute the great work you've been doing.
Yes. Thank you, and we'll see you inside one of these other virtual rooms later in the day. Thank you again.
Oh, and lastly, we encourage everyone to go to the chat room at after this session as well.
Yeah.
I had a few questions coming up here. I think we will just answer them now. When you close down this session, will I still be able to answer them?
I believe they will go away.
So hang in there. Hopefully I can answer it really quickly.
Right. Well, I will keep my end open if that's possible. I'm not sure how we how the platform shuts us down, but our
if you end it, the questions and the chats will all go away.
I think we have a minute or two that we could maybe squeeze it in. I have no idea.
I answered most of my questions. I typed them.
Yeah, Regin, you can answer the questions, please. We can keep it open for a couple of more minutes.
I think the Florida climate was for the house question. And I think you're muted.
Yeah, I just want to thank everybody too. I think it's very important. One of the reasons I actually took the job here at NDSU was that they still had an architecture program together with engineers. But as you know, all schools are separating architecture out of engineering. I never really liked that. I think it's very important that architects understand those aspects that all of you are talking about. So I enjoyed very much that I was part of this session. It was, of course, a very different presentation that I did. But I just think it's very important that we somehow work together. Or without that, designers will never really understand how to make better buildings.
Good. Well, thank you all, and we'll hopefully see you all in one of the chat rooms after this.
By the way, Henry, thank you. Thank you for organizing this. Thank you for running it. And thanks a lot for answering 4,000 of my emails. Really, thank you.
It's okay. I grew up talking to pipes, and it was a sort of like plumber and sort of builder in that way. So that I'm not usually on the presentation side, but I kind of figured that somebody should do it, and so I fumbled my way through it that way. And but I'm glad I had talent here, and I think that each one of you needs to be, give yourself a chance to engage with ACES for this year and next year and onward.
Thank you so much.
Okay, good.
Thank you, everyone.
Yeah, thank you.